Hi, welcome to this lecture on input and output. Here's an outline for this lecture. We'll first talk about the concepts of input and output of a program, and then we will discuss a form of output that we're already familiar with, which is standard output, and then we will discuss a new form of input called standard input, and then we'll talk about concepts such as redirection and piping, which are closely related to standard input and output. And then we will discuss two new forms of output, namely standard drawing and standard audio. So let's get started. You can think of a computer program such as my_program.py as a box that is shown here, receiving some kind of an input from the user and producing some kind of an output. Now, a program that doesn't receive any input from the user or produce any output is a useless program. So the concept of an input and output of a program is extremely important. In this course, we're going to consider several forms of input and several forms of output. For input, we are going to consider command line input, which we've already seen. Right? That's the mechanism that we've been using so far to provide input values to our programs. And the way we do that is by simply listing them after the program name and accessing them inside of the program using the sys.argv list. So if you want to get hold of the first command line argument, you simply say sys.argv square brackets 1. And if you want to get hold of the nth command line argument, you would say sys.argv square brackets n. Okay. Now, command line arguments have their limitations. So, for example, with command line arguments, you cannot process arbitrary amounts of input. For that, you need something like standard input, which makes it possible to write programs that can process arbitrary amounts of input, and standard input also allows you to interact with programs. Okay. So, we will consider standard input in this lecture. Now, standard input itself has limitations because it just represents one input stream. So what if you want to write a program that processes multiple input streams? For that, you need to go beyond standard input and you need to talk about file input. And file input is what makes it possible to write programs that can process multiple input streams. Right? And we'll save file input for a future lecture. Now, for output, we're going to consider standard output, which is something that we are already familiar with to some extent. That's the mechanism that we've been using to print output from our programs to the terminal window. Okay? The way we do that is by simply calling methods or functions such as stdio.write and stdio.writeln. So these guys take arguments such as a string s, and write simply writes it out without a new line character at the end, whereas writeln writes that string s out with a new line character at the end. Okay? Now, in this lecture, we are also going to consider other forms of output, such as standard drawing, which makes it possible to work with graphical representations of images. So this is what will allow you to draw something on the screen. Okay, so we'll discuss that in this lecture. And then we will also talk about standard audio, which is what lets you write programs that create and manipulate sound. Okay, and then in a future lecture, we'll talk about how you use file output to write programs that process multiple output streams. Because standard output has its limitations in that there is just one output stream that you can work with, right? Which is the terminal window. But what if you want to write a program that processes multiple output streams? Well, in that case, you have to go beyond standard output and consider file output. So we will do that, but that is something that we're going to do in a future lecture. So in this lecture, for output, we're going to focus on standard output and we'll learn some new concepts here. And then we will also discuss standard drawing and standard audio. Okay. So let's first start with a program called randomsequence.py. And what this program does is it takes an integer command line argument n, and it simply writes to standard output or the terminal a random sequence of n floats. All right? And these random floats are obtained from the interval 0 through 1, where 0 is inclusive and 1 is not. And this program deals with command line input. So that's this one input n as an integer, and it deals with standard output. So the output that it produces is standard output because it simply prints the n random floats to the terminal or standard output. Okay, so let's go through the program. It's very simple. So we import three modules, random, stdio, and sys, and we are familiar with all of these. And then we receive a command line argument as an integer, and we call it n. And then we have a simple loop where I goes from 0 all the way up to n minus 1. So we are performing n iterations. And in each iteration, we simply make a call to random.random, which we know generates a random number between 0 and 1. Notice that 0 is inclusive and 1 is not. And we write that random number using stdio.writeLn. So what this program does is it correctly writes n random floats from the interval 0 through 1. So if you run this program with n equals 10, it prints 10 floating point numbers from the interval 0 through 1. Right? And if you run it with 100, it's going to print 100 floating point numbers from the interval 0 through 1. So this is a very simple program that deals with command line input, and it deals with standard output. Okay, command line input and standard output. Right? Okay. Now let's talk about some new concepts relevant to standard output. So here is the API for the Stdio module, and the functions that are shown here are relevant to standard output. Okay, and the first two we are already familiar with. So write is the function that takes an argument such as x and simply writes it out, okay, to standard output or the terminal. And writeLn takes that argument x and it writes it out to standard output, but with a new line character at the end. Right? And these two functions we are already familiar with. In addition, Stdio also has a function called writef, which stands for formatted writing, and that takes arguments arg1, arg2, and so on, any number of arguments, and it writes them out to the terminal, but using a format that is specified by the first argument fmt for format. Okay, so it takes a whole bunch of arguments that it writes to the terminal according to the format that is specified by this format string. Okay, so the first argument is the format string. So let's look at some examples. In the simplest form, writef simply takes two arguments. The first argument is a format string that describes how you want to convert the second argument into a string for output. Okay. And here is an example of that. So we say stdio.writef, and the first argument is the format string. Okay, so we are saying as a string literal pi is approximately, and then here comes some syntax. Okay, this is basically the format specifier, %.2f, and what it says is it provides the rule for formatting this argument. Okay, this argument. The argument is simply mat.pi. And then what we are saying in this rule is that we want to print this value up to 2 decimal places. So 0.2 means up to 2 decimal places. And F stands for the fact that this is a floating point number. And % is just part of the syntax. So % something means a placeholder, and that placeholder gets replaced by the argument value. So in this case, mat.pi, the argument is going to substitute in here, and it's only going to have up to 2 decimal places. Okay? And if you look at the output, this is what you see. Pi is approximately 3.14. So this part of the string is that part of the format specifier, and then this period is that one here, and then there is a new line character at the end, so there is a new line here. And then this part here is basically how mat.pi was formatted by this rule. Okay, and as you can see, pi has been printed here with up to 2 decimal places. So if you wanted pi up to 5 decimal places, you would simply change this to 5 instead of 2. Okay, so that's how formatted printing works. Now, stdio.writef function can take more than 2 arguments, right? In which case the format string will have a format specifier, this kind of a % syntax, for each additional argument. Okay, and let me give you an example of that. So here we are saying stdio.writef, and here is the format specifier, and notice that there are 3 format specifiers here. That's the first one, that is the second one, and that is the third one. Okay, 3 format specifiers, and hence we have 3 arguments. So the first argument is going to replace this format specifier. The second argument is going to replace this format specifier. All right. Now the 10 here means that we want math.py up to 10 decimal places. F stands for floating point number because math.py is floating point number. Here D stands for integer because 5 is an integer. And then finally this 9 here is going to substitute in for this format specifier. Okay, so when you look at the output, this is what we see. The first guy 5 takes place of this guy, so we see the 5th decimal digit of, and then math.py takes the place of this format specifier but up to 10 decimal places, and then finally 9 takes the place of this format specifier, so that's why you have that. And the period is simply this period here, and then there is a new line character here, right? So that's how writef works. The first argument is a format specifier that tells how the rest of the arguments need to be formatted. All right? Okay, so now let's consider a new form of input. So far we've discussed a command line input. All right? Now command line input has its limitations in that you can't really use it to process arbitrary amounts of input. All right, and it is also quite tedious to simply list all the input right next to the program name every time you run it. That's rather tedious, so we want to consider a different form of input. So the standard input stream or standard input is basically an abstract data stream that can be either empty or it may contain a sequence of values that are separated by white space. Okay. So it's basically a sequence of values, right, separated by white space. And the end of such a stream is marked by what is called the end of file or EOF character. Okay, and that is specified on a Unix-like system using the key combination Control-D or Control-Z on Windows-like systems. So these key combinations simply map to EOF. Right? So the input stream is nothing but a sequence of values separated by white space, and then at the end of the stream there is the end of file character. Right? Now we are going to use the standard IO module also to deal with standard input. Okay? So we've used functions from here to deal with standard output. We can also use this module to deal with standard input. Right? This module makes it really, really easy to work with standard input. Now keep in mind that a program that processes data or reads from standard input stream consumes all the values. Okay, so it can only go in the forward direction consuming all the values, and it cannot back up and read them again. Right? So you only have one shot at the input stream, at the values in the input stream, and you keep reading the input stream in one direction and you can't rewind back. Okay, so keep that in mind. And if you want to save the values that you're reading from the input stream for whatever reason, you need to store it in a collection of some sort. Okay, so what I'm showing you here is the API for the stdio module that is relevant to standard input. Okay, so all these functions are functions that are relevant to standard input. For example, you can use this function stdio.isEmpty to check if the input stream is empty or not. If it is empty is going to return true and false otherwise. Okay. And then you can use this function here, readInt, to read a token and as an integer. Okay. So you can read an integer value from the input stream from standard input simply using this function readInt. Similarly, you can use readFloat to read a float, read bool to read a boolean, read string to read an entire string. And then you can use this function to check if there is a next line in the input stream or not. And if there is one, you can read it using this function stdio.read line. And then you can use this function here to read everything from input stream as a single string. Okay? And then you can use these guys to read several integers, floats, bools, or strings from standard input. And when you use these functions, the values are returned to you as a list. Okay? So for example, read all ints will return all the integers from standard input as a list of integers. And read all strings will read all the remaining tokens and return them as a list of strings. Right? And then finally you can use this function to read all the remaining lines in standard input and return them as a list of strings. Okay? All right. So now let's take a look at a program called 20questions.py. And what this program does is it generates a random integer, and then what the user is supposed to do is guess that particular integer. Okay? So the computer is going to think of a number, a random number, and the user is repeatedly going to guess what that number is. Okay? Now, if the user's guess is too low, then the program will say that it was too low, in which case the user can adjust her guess. And if the guess is too high, the computer will say so. And if the guess was correct, then the computer will print the message "you win" and exit the program. Okay, so that's the idea. And the computer is going to think of a random number between 0 and a million. Okay. Now there are different strategies that one could use in guessing the correct number. The not so smart strategy would be to start at 0 and go in increments of 1, or until the correct number is found. Right? But that is not a very smart strategy, because you are going to have to guess too many times in the worst case. Okay. So a better strategy would be to consider the middle number as the first guess. So since the computer is going to think of a random number between 0 and a million, a good guess would be to start with 500,000. Okay? And if the computer says that this is too small, then you know that the correct number is not between 0 and 500,000, but it is between 500,000 and a million. So then the next guess could be something like 750,000. Okay. And if now the computer says that this guess was too big, then the user can try a number that is in the middle of these two guys. Okay. And so on and so on and so on. So that's a much better strategy. And it turns out that if you actually use that strategy to guess a number between 0 and a million, then in the worst case you only have to guess 20 times. 20 guesses, right? And hence the name 20 questions. Okay? So even with a range as big as a million, in the worst case, you'll only have to guess 20 times using this clever strategy, right? Okay, so let's see how this program works. So we import a couple of modules, random and stdio, and then range is set as a constant to a million, right? And then the computer is going to generate a random number called secret from the range 1 through a million, right? And this is the secret that the user is supposed to guess. And the computer goes about printing a message saying that I'm thinking of a secret number between 1 and this and a range, which is a million. And then what we do is we start with guess equals 0. Okay. notice that the initialization of guess is such that it is outside of the allowed range of numbers. Okay, so the computer thinks of a number between 1 and a million. Okay, and initially we start with a guess of 0. So 0 is clearly not equal to secret when we start, right? And the computer then asks what the user's guess is. So that's this message, and then comes something very interesting. So we make a call to the function readInt from stdio. Okay, now when such a function is executed, the program simply stalls or waits for input, right? So these are called blocking calls. So readInt, a call to readInt simply will wait. Now the user at that point is supposed to type in a number interactively, and when that number is fed, then this function is going to return that number, and that's what gets assigned to guess. So that's the initial guess. And then we compare that guess with secret. If guess is less than secret, then we print the message too low. And if guess is greater than the secret, we print the message too high. And if it was a match, we print you win. Okay? Now when it is a match, then next time around this condition is going to be false, because guess is going to be equal to secret and we are outside the while loop. But if guess is not equal to secret, then we keep going, right? Now we read another input from the user and compare that against the secret, and so on and so on and so on. So that's how this program works. So let's see how it runs. So we say Python 3 20 questions.py, that's how you run it. And the program prints this message that I'm thinking of a secret number between 1 and a million. That's from, so this line of output is from here, right? And then the computer asks what the user's guess is. So let's say the user, and so at this point, as I said before, the program just waits for input. And let's say the user types in 500,000 and hits enter. Then the program comes back saying it's too low. So now the user knows that she needs to guess between 500,000 and a million. So a good strategy is to guess 750,000. Okay, and then when the user hits enter, then the program comes back with the output too high. Now the user knows that the number is between these two guys. Okay? So the next good strategy would be to guess 625,000. Right? And the computer says even that's too big. So now you know what you need to do. Guess a number that is at the halfway point between 500,000 and 625,000. Okay? So you keep doing this, and at some point you're going to, if you follow this strategy, you're going to guess the secret. Okay? So in this case, let's say that was the guess, and that was also the secret. So in that case, it's this message that gets printed out. So that's what you see here, and the while loop is done, right? And you're done with the program as well. So as I said before, if you use this kind of a strategy, then in the worst case, you're only going to have to make about 20 guesses. Okay? Now notice that this program is something that you could not have written with command line arguments. Okay? Because here you simply don't know how many guesses the user is going to make. Right? So you have to work with something like standard input or interactive input. Right? So this is a program that you simply could not have written with command line input. Okay, here's another program where we make use of standard input. This program is called average.py, and what it does is it reads floating point numbers from standard input, and any number of them. So the program doesn't assume any particular number of numbers. So it can deal with any number of numbers, and what it does is it calculates the average of those numbers and it prints it out. Okay, so it writes to standard output the average of those floating point numbers, which are fed to the program via standard input. So let's go through it. We import stdio. Because we are going to use it both for standard input and standard output. And then we initialize a couple of variables. Total is going to keep track of the sum of the input numbers, and count is going to be the number of numbers. Okay, so let me make a comment here. So the first line is going to be the sum of numbers, sum of the floating point numbers fed via standard in, and count is simply going to be the number of numbers that are going to be fed by the user, which of course we don't know in advance, right? Okay, and then what we have is this while loop where we say as long as the input stream is not empty, so remember isEmpty is a function from stdio that returns true when the input stream is empty and false otherwise. So we're saying if it is not true or not empty, then do these things. So what are we doing in the body of the while loop? We first get the next number from standard input by making a call to the read float method from stdio. Okay, so that's going to fetch a floating point number from the input stream from standard in, and that is what gets assigned to value. Okay, so again, this is a blocking call. When this function is called, the program simply waits for input, and the user types in an input, and that's what is assigned to value. All right. Okay, and once we get that value, we simply add it to total, because total simply keeps track of the sum of all these values. So we add it to total, and then we increment count by 1, because we just read a new value, right? And we keep doing this as long as the input stream is not empty. And at some point, the user is going to send the end of file signal by either typing Control-D or Control-C, and that's when stdio.isEmpty is going to return true, and not if true is false, and we are out of the while loop. Okay? So it's when isEmpty sees EOF or end of file signal, that's when the while loop terminates. And once we are out of the while loop, what we do is we calculate the average by saying average is the total divided by the number of numbers, and then finally we simply print the average value. We say the average is the value in AB in this variable turned into a string and concatenated with this string literal. Right? So that's the program. And so notice that this program can process any amounts of input. So it can calculate the average of any number of numbers. Okay. So here's how we run it. We say python3 average.py, and when you do that, the program simply waits for input. All right. So it's basically blocking at this call stdio.isEmpty, and then let's say we type a number 10 and hit enter. So since this was 10 and not the end of file signal, this returns false, and not a false is true, so we are inside. So we end up reading 10 via this call to read float. So value is now 10, and 10 gets added to total, so total is now 10. And since we have read a number, we increment count by 1, so count is now 1. Okay? And then next time around, the user types in 5, and that is not the end of file signal, so we end up reading it here and assigning it to value. Value gets added to total, so total is now 15, count is now 2, and then the next time around the user types 6. So again, it is different from end of file, so that gets read in by read float, and it's assigned to value, and that value is now added to total, which is now 21. Okay. And then the user continues providing more numbers such as 3, 7, 32, and so on. And then finally, the user sends the end of file signal. So the user types in Control-D. So this, remember, is end of file signal on Unix-like systems. So when the user types in end of file signal, that's when stdio.isEmpty returns true. Okay, and not if true is false, so we are out of the while loop, and we calculate the average as whatever the total is of all these guys divided by count, and the program comes back with the average as 10.5 in this case. Okay. All right, now let's talk about some important concepts that are related to standard output and standard input. Now when you run a program, we can add the directive greater than sign to the command, and when you do that, what we are doing is we are redirecting the standard output of that program to some file. Okay, so we can save the standard output of a program into a file for later use, right? And here, and it's illustrated here. So we run the random sequence.py that we discussed before as such, giving it a command line argument of 1000. So when you run this command just by itself, ignoring this part, what it does is it prints out to standard output 1000 random numbers between 0 and 1, right? So that's how this program works. But now what we are doing is we are taking the standard output and we are redirecting it. So this is this directive that I'm talking about here. All right. So we are redirecting the standard output of this guy into a file called data.txt. So when you do this, you're not going to see the output from this program on the screen. Instead, all the output, the standard output, is going to be saved in this file. Right? And then if you go about inspecting that file using the Unix command head, so what we're saying here is I want to look at the first 5 lines of the file data.txt that was produced here, right? And what I see here are the first 5 lines in that file, and they are simply 5 random numbers from the interval 0 through 1, because that's what this program does, right? It prints 1000 random numbers between 0 and 1, and here I'm simply looking at the first 5 using the Unix command head, right? And this number simply specifies how much of the top of that file you want to look at. So -5 means the first 5 lines, -50 would mean the first 50 lines, right? Okay, so that's how you take the standard output of a program and save it into a file so that you can use that later if you want, or maybe as an input to another program. Okay? And then similarly, what we can do is we can use this directive, the less than sign, along with a command to redirect the standard input, okay, so that the stdio reads data from a file instead of the terminal. Okay, so when you're working with standard input, and if you have a program that processes arbitrary amounts, large amounts of input, then you don't want to be sitting there and typing that input manually. That's just tedious. Even doing it once is very tedious if you have lots of data, input data, and doing it many times makes it even harder. So what you want to do is you instead want to save your input in a file and redirect that file using this directive as input to the program. Okay, and when you do that, stdio simply reads from that file. It doesn't even know that you're using this directive. It still thinks that its input is coming via standard in, right? So it doesn't care whether that input is fed interactively by a user or it is being fed in using this redirection operator, right? And here's an example of that. So we are running the average.py program here. This is the program that we discussed before, and when we do this, what we are also doing is we are redirecting this file data.txt that was produced here using the less than directive, right? So we are saying make this file be now the standard input of this program. So when you do this, I don't have to type in the input values interactively, right? So whatever the numbers are in this file becomes the input of this program, and the program comes back with the average of those 1000 numbers in data.txt, and that's what you see here. Okay, so the program doesn't even know that you're doing something like this. It still believes that the input is coming via standard in. Right? Now the question is, when you run a program like this using this less than directive, how does the program know when to stop? So in other words, where is the end of file signal? Because that's what eventually terminates this program, right? So at the end of the input, it needs to see an end of file for it to stop. Where is that when you're using redirection? Well, it turns out that every file on your file system, every file, in addition to all the data that it contains, at the very end it has the end of file character. Okay, and data.txt is no exception to that rule. It's just a file, so at the very end it has an end of file character. So when the program, when average.py sees this character, or to be more specific, when stdio.isEmpty sees this particular character, that's when it's going to return true. Okay, and that's when you're going to be out of that while loop and calculate and print the average value. Right? So that's how things work when you're using the redirection operator. Now, the standard output of one program can be mapped to the standard input of another program using the pipe directive. Right? So using this directive, you can take the standard output of some program. So on the terminal, you can take some program 1 and make its standard output be the standard output of another program 2, and then you can take the standard output of that to be the standard input of another program, so let's say program 3, and so on. Okay, and here's an example of that. So we run random sequence.py from before with n equals 1000. So remember, that is going to produce 1000 random numbers, and it's going to write it to standard output. But we're saying, make that standard output of this program be the standard input of this guy, the average program, using the pipe operator. So when you do that, those 1000 numbers are not going to be written to the screen, but they're going to become the standard input of this program. And this program simply averages those numbers out and prints the result. Right? So here again, this program still believes that it's getting its input from standard in, right? And in fact it is. I mean, that's what is going on here. The standard output of this guy is basically the standard input of this fellow, and that's because of the pipe operator. Here's another example. So we run the same command again, and then we pipe the output of average to a Unix command called WC. WC stands for a word count. And the way this program works is, it receives some input from standard in, and it simply reports on the number of lines, the number of words, and the number of characters. Right? That's how WC works. It outputs the number of lines, the number of words, and the number of characters that it saw in its input. Well, what was its input? Its input was a string like this, right? But how many lines of output is that? It's exactly 1 line. How many words of output is that? Well, that's word 1, word 2, and word 3. So that makes sense. And how many characters is it? Well, if you count it up, you're going to see 26, right? So what is shown here is that you can chain any number of these commands together using the pipe operator. And the way the pipe operator works is that it makes the standard output of the command to the left be the standard input of the command to the right. And here is another example where we show how we work with command line input, standard input, and standard output. Right? So this program is called rangefilter.py, and it accepts 2 command line arguments as integers, low and high, and then it's going to read integers from standard input until it sees the end of file character. And for output, what it's going to do is it's going to print only those integers that are within this range, low to high. Okay, meaning if an input that it saw from standard input is between low and high, then it's going to print it. If it's outside of this range, it's not going to print it. Right? And low and high are both inclusive. So let's see how the program works. We import our usual modules, and then we get the 2 command line arguments, low and high, as integers, and then we are saying, as long as the standard input is not empty, read an integer from standard input assign it to value, and then check that value to see if it is in the interval low through high. So if value is greater than or equal to low, and if it is less than or equal to high, meaning we are checking if value is from the closed interval low to high. If so, we simply print it out. Okay, so we only print the values that are in the interval low through high. And we keep doing this until we have processed all the input from standard input, right? And at the end, we simply write the new line character. So let's look at some input and output. So here we run this program range filter.py with 100 for low and 400 for high. All right, and then for input, we provide all these numbers. So these guys are all standard input. Okay. So this is all standard input, and this is basically the output. And why do we see just these numbers? Well, 358 is in the range 100 through 400. 165 is also in that range, and so on and so on. We don't see 55, for example, because it is not in this range. Okay, so the output numbers are simply the numbers from the range low through high. So this is a nice program that shows how you work with command line input, standard input, and standard output. Here is another run where we show how piping works. So what we do is we take the Unix command sequence to generate a sequence of numbers from 1 through 100, right? In steps of 1. So sequence 1 through 100 is just going to generate 1, 2, 3, 4, 5, and so on, all the way up to 100, and it's going to print it to standard output. But then, because of the pipe operator, all that standard output becomes standard input to this command here. Now, shuff is a Unix command which simply shuffles its standard input. So these 100 numbers are going to be shuffled and written out to standard output. But then that output, we make it to be the standard input of range filter, with this for low and this for high. So we have, so what do we have for standard input of range filter? We have 100, we have the first 100 integers, 1 through 100, shuffled, right? So that's the standard input of range filter. And the program comes back with this output. Now, why are we seeing exactly these numbers? Well, these are the numbers that are in the range 25 through 75. And how many numbers do we expect to see here? We expect to see exactly 51 numbers, okay? Because you have 51 numbers from the closed interval 25 through 75. Here is another run of the same program with a slight modification. So we take a sequence which is the first 1000 integers, shuffle it, and then make that be the standard input of range filter, where low is 250 and high is 750. Now, how many numbers do we have? So from 1 through 1000, how many numbers do we have that are in this interval 250 to 750? 501. And so that's why when we send the output of this fellow to WC with this argument minus v for just the number of words, we see exactly 501. Okay, so WC is the command that we saw in the previous slide, but here we are saying we don't really care about the number of lines or the number of characters. I just want the number of words to just verify the fact that there are 501 numbers between 250 and 750 if you're looking at an input sequence that is 1 through 1000. Okay, and that's confirmed here. Right? Okay. So now let's look at a new form of output called standard drawing. And for this, we're going to make use of the Std Draw module from the authors of our text. And that module provides us an abstraction for producing drawings as output. Okay? And here is an API for this module. It supports two categories of functions. The first one called drawing functions, and the API for that is shown here. And then it also supports another category of functions called control functions, which we will see in the next slide. Okay, so let's look at some of the drawing functions. So these are the functions that you would use to draw something on the screen, right? So for example, you could say Std Draw dot line and give it 4 arguments, x0, y0, and x1, y1. And what this function will do is simply draw a line between x0, y0, and x1, y1. So it will connect up the 2 points, x0, y0, and x1, y1. You can use this function to simply draw a point at xy. You can use this function to draw a circle of radius r having a center xy. You can use this function to draw a filled circle. So the circle is going to have a center xy and radius r, and it's going to be filled with some color that you specify with one of the control functions that we will discuss later on. And then you can use this function to draw a square. So it takes 3 arguments, x, y, and r, and it's going to draw a square that has dimensions 2r by 2r and is centered at xy. So that's how square works. And then you can draw a fill square, you can draw a rectangle, you can draw a fill rectangle, a polygon, a fill polygon, and you can also write a particular text s at the coordinates xy using this function. Okay, so these are the drawing functions that the Std Draw module supports. In addition, it also has control functions. So here is a list of the control functions from the Std Draw module. You can set the size of the canvas using this function, and that simply sets it up with a size of w pixels and h with a width of w pixels and height of h pixels. Okay? So you're basically setting up a canvas that is w by h pixels. And then you can use these 2 functions to set up the coordinate system. So for example, if you say set x scale 0, 1 and set y scale 0, 1, then your canvas has this coordinate system. So it is 0, 0 here and it is 1, 1 here. Right? So this point then would be 0.5, 0.5. Right? So these 2 functions allow you to set the coordinate system. And then you can set the pen radius to this value. You can set the pen color to this value. So here C is basically a color object. And then you can set the font to that. You can set the font size to that. And then you can clear the screen using this function. And you can clear it with a particular color. So this color, for example, could be the color object representing red, in which case you paint the whole canvas red, right? And then you can show the drawing on the canvas using this function, and this argument specifies for how long you want to wait in milliseconds. Okay, so when you do this, it shows the drawing on the canvas, and then it simply waits for t milliseconds. And then finally, you can take the drawing that you have on a canvas and save it into a file, okay? Using the save function. And you save it either as a JPEG or a PNG. Okay, so those are the drawing and control functions from the Std Draw module. Let's look at an example where we make use of the module. So this program is called plotfilter.py, and what it does is it receives input via standard in, right? And the input consists of the x and y scales for the canvas, and in addition, it contains the coordinates of points, right? And what the program is going to do is simply draw these points on the screen using Std Draw, right? So it's going to set up the scale using the scale information that it receives from standard input, and then it's simply going to read until end of file the coordinates of a whole bunch of points and plot them on the screen. Okay? And it's going to make use of the Std Draw module to do that. Okay, so let's first go through the program. So we import Std Draw and Stdio. Std Draw because we want to draw something on the screen, and Stdio is because the program gets its input from standard input. And then what we do is we get the scale information from standard input using calls to read float. So the first two calls basically gets us, so we want to set up a scale for our canvas. So the first 2 points, x0 and y0, is going to be this value, x0, y0. And then this guy is going to denote this point, x1, y1. Right? So the first 4 values in standard input is essentially providing the scale for the canvas. And once we have those values, we make calls to the 2 control functions, set x scale and set y scale, giving it those values. Right? So x scale goes from x0 to y0, and y scale goes from y0 to y1. So that's what we're doing here. And then we set the pen radius to 0 by making a call to the set pen radius function from the Std Draw module. And a value of 0 for argument simply means we want the pen radius to be 1 pixel width. Right? So 0 doesn't mean nothing as an argument to set pen radius. It simply means pixel width. Right? And then as long as standard input is not empty, what we do is we read a pair of numbers using read float. So x is a float, y is a float, and that represents a point. All right? So we read a pair of numbers which represents a point, and then once we have the x and y coordinates of that point, we simply draw it using the point function from the Std Draw module. Okay? And when you do that, it simply draws a point on the screen. And then we go read the next point, get its coordinate, draw it on the screen. Get the next one, draw it on the screen. Next one, draw it on the screen, and so on and so on and so on. And at some point, the input stream is going to be empty, in which case we are out of the while loop and we make a call to show from the Std Draw module, which is what will render this canvas on the screen. Okay? So that's how the program works. Let's look at some input and output. So here I'm simply showing you, using the head Unix command, the top 5 lines of the file usa.txt. This is just a data file that contains the GPS coordinates of point in the US, right? And the first 4 numbers essentially specifies the scale. So this is x0, this is x1, this is y0, and this is y1. Okay, so what we're saying is the smallest value of x coordinate is that, the largest value is that, the smallest value of y coordinate is that, and the largest value of y coordinate is that. So the first 4 numbers in this file essentially sets the scale for the canvas. And then what you have are, so each of these lines is simply xy values. Right? So a whole bunch of xy values, and at the end, of course, you're going to have the end of file signal inside of usa.txt. So here, I'm only showing you the first 5 lines, and then you have many, many lines, and at the end of file. Okay, so that's the file. And now, if I run this program, plotfilter.py, and redirect this file into it using the redirection operator, okay, then what the program does is it simply produces this plot, right? So it first reads the 4 numbers at the top of the file and sets the scale, right? So this is like x0, y0, and this is x1, y1. And then the program goes about reading these points and plotting them on the screen. So each point that you see here is basically a pair of numbers from this file, right? So that's how this program works. It's a very interesting program that shows how you use the Std Draw module to do something interesting. And now notice that if you want to render the points from another country, you really don't need to change this program at all, right? You can simply code or create another file for that country, and you can store the points for that country in that file, right? So you will not have to change the program at all just because you want to plot a map of some other country. Okay? So you can run exactly the same program with a different data file one for each country to produce a plot per country, right? So that's the power of writing, like programs that are data driven. Okay? So you really don't need to modify a program just because you're processing a different data set. Okay? Here's another example where we make use of the Std Draw module. This program is called bouncing-ball.py, and it simply draws a bouncing ball to standard draw. Right? So let's see how it works. We import Std Draw, that's the only module that we use here, and then we set up two constants, radius to 0.05. So this is going to be the radius of the ball that we want to draw. And dt is going to denote the time delay in milliseconds. So we simply set it to 20. And then we set the x scale to go from -1 to 1. So our canvas is going to go from -1 to 1 on the x-axis. And on the y-axis, it's also -1 to 1. Okay? -1 to 1. So that's the scale. So this point here, right in the middle, is simply 0, 0. So that's the scale. And then we set, we create these variables rx, ry for x and y coordinate of position to these values, and then vx and vy for the x and y coordinates, the velocities of the ball to these values. Okay, so v stands for velocity, r stands for position. And then we say while true, so this condition is quite interesting. So true is always true. So this denotes an infinite loop. So this program, when you run it, it's going to run forever. It's going to have this ball bouncing around forever. Okay, so what are we saying here? We're saying if the absolute value of rx plus vx plus the radius of the ball, if it is greater than 1, then vx equals -vx. So what we are saying here is that if the ball reaches the edge along the x-axis, meaning if it gets here or if it gets here, make the velocity to be the negative of its velocity, meaning make it rebound, right? So if it goes over the edge this way, we change the velocity to that direction, the x velocity. Similarly, if the ball hits this right wall, we simply change its x velocity to be that, right? So that's what we do here. What about this line of code here? Exactly the same idea, but along the y-axis. So if the ball hits the top wall, then we make its y velocity to be the opposite of what it was. And if it hits the bottom wall, again the same thing. The y velocity is changed to the negative of its current velocity, current value. Okay, so that's that. And then we simply update the position of the ball. We say the new x value for the ball is the old x value plus the x component of the velocity. You can think of this as the x component of the velocity times some unit time interval. Okay, and similarly here times some unit time interval. So when you do that, you're basically adding position to change in position, position to change in position. Right? And when you do that, on the left hand side, what you get is the new position, the new x position, the new y position, right? And similarly, even here, it might seem like you're adding apples and oranges. That's not true. So you're really adding position to velocity times some a unit time interval. So unit time. So here again, unit time. So unit time, right? So when you multiply velocity by time, you get position, right? So again, we are updating the x component and y component of positions by saying that the new x component is the current x component plus the change in position, okay? And the same for ry. And once we have the new position, we simply draw a filled circle to represent a ball at the new position rx and ry. Okay, so we draw a filled circle with that as the center and that as the radius. So that's the radius of the ball, that's where it is, that's the center of the ball. And then we make a call to the show function from Std Draw and we give it dt as an argument. So what that does is it will simply draw the ball on the screen and wait for 20 milliseconds because that's what the value of dt was. Okay? And then we perform the next iteration. So dt essentially is the frame rate. It's the time between two updates of the screen. Now, before I show you some output, let me just point you to this commented line. Okay? So if you want to run this program and get the feel of a bouncing ball, you really need to uncomment this line. Okay? I have left it commented here because only then you get to see this kind of an output where you see a trail of the ball. Okay? So you see a trail of the ball because this line is commented. So if you uncomment it, you will not see a trail, but you will only see the ball at different instances of time. Right? All right. So that's standard draw. Now let's look at another type of output, namely standard audio. Now to obtain a digital sound, what we need to do is sample a continuous sound signal, which is typically represented by a sine curve, at regular time intervals. Okay, so what that means is you have an analog signal, right, representing some sound, and you want to turn it into a digital signal. So the way you do that is by sampling this analog signal. So you discretize it. Right? So you look at these discrete intervals and you simply save those points, right? And a collection of those points at these discrete time intervals is what we call a digital representation of that analog sound signal. Right? And and this process of discretizing an analog signal is also called sampling the signal. And a widely used sampling rate is 44,100 samples per second, right? So that's what is fairly popular. So a digital sound is nothing but a list of real numbers between -1 and 1, right? Because if you have a sound signal that is represented by a sine wave, then the y value is strictly between -1 and 1 because the sine function is bounded by -1 and 1. And if you discretize it, using the idea that I just described, then what you're storing for this sine curve is basically the values of these points, which are all between -1 and 1. Okay? So the digital sound then is nothing but a list of numbers which are each between -1 and 1, right? Now it's the Std audio module that we're going to use as an abstraction for playing, manipulating, and synthesizing digital sounds. And here is the API for this module. The first function here, play samples, takes a list A of floating point numbers, and it simply plays those sound samples, all right, on your system's audio hardware. And then you can also call this function, stdaudio.playFile, and give it a wave file as an argument, and it will simply play that wave file, right? And then you can play a single sample using this function, play sample. So that simply takes a single floating point number s as an argument and plays it. And then if you have an array of samples, A, you can save it in a file F in wave format using this function, right? .save. And then finally, you can wait for the currently playing sound to finish by making a call to the wait function, right? So, you use this function to basically flush the audio out before your program terminates, right? So these are the functions that the Std audio module supports. So let's look at a very nice example of this. So this program is called Play That Tune. And what it does is it reads sound samples from standard input and simply plays the sound to standard audio using the standard audio module that we just discussed. So we import some modules, math, std array, and stdio, which we've seen so far, and then the new std audio module that we just talked about. And then we initialize three constants, SPS for samples per second to the most popular sampling rate, which is 44,100. And then we set the value of concert A to be 440. So that's the frequency of the concert A note. And then we say that the number of notes on a scale is 12. Okay. And then we read values from standard input, and this is how that works. So as long as standard input is not empty, we read a pair of numbers. Okay, the first number represents the pitch of a sound, and the second number is the duration, meaning what note do we want to play, and for how long do we want to play that note. Okay, so we read that as a pair of numbers from standard in, both as float, the first one as an integer and the second one as a float. And then what we do is, given the pitch, we turn it into a frequency in hertz using this formula. All right, so let's think about this formula carefully. So it says hertz is concert A times 2 to the power pitch divided by notes on a scale. So if pitch is 0, for example, what is this quantity going to be? Well, that's 0. What is 2 to the 0? It's 1. So concert A times 1 is simply concert A. So what we're saying is a pitch of 0 corresponds to hertz of 440. That's concert A. What about let's say a pitch of 12? Well, if this is 12, then 12 over 12, notes on scale is 12, so this is simply 1. What is 2 to the power 1? It is 2. Concert A is 440, so 440 times 2 is 880 hertz. Okay, so 0 corresponds to concert A, and 12 corresponds to a note that is exactly 1 octave higher than 440. And now 24, you can guess it's going to be a note that is 2 octaves higher than concert A. So it's going to be 440 times, right? So it's going to be 440. So if this is 24, it's 2 to the power 2. So it's times 4, and so on. Okay, and any value between 0 and 12, such as 0, 1, 2, and so on, all the way up to 11, is going to give you all the notes on a chromatic scale, right? With some value for frequency. So what this formula is doing is it's simply turning a pitch, which is a number between 0 and 12, or higher, to a frequency, right? And then what we do is we calculate n as the samples per second times duration. So duration, remember, was how long the user wants to play a particular note. We simply multiply that with samples per second. So n denotes the number of samples that you need for that time interval, right? Per second you need these many samples. For those many seconds, you need n samples. And once we have n, we simply create an array using the create1d function that we talked in a previous lecture. So we use the create1d function to create a one-dimensional list of size n plus 1, where everything is initialized to 0. And that's the array that we call note. Okay. So what is note going to contain? The note is going to contain n samples corresponding to this sound that the user wants to play. A sound that has some pitch and has some duration. Okay? And then what we do is, in this for loop, we sample a sine curve. So we simply sample a sine curve of the desired frequency. Okay? A sine curve of frequency hertz. So we sample it at time intervals I, using this formula, mat.sine and blah blah blah. Okay, so that simply has the effect of sampling the sine curve at time intervals given by the variable I. Okay, so we do that for I going from 0 all the way up to n. So once this for loop is done, we have our list node, which is basically a digital representation. So this is a list that's a digital representation of an analog sound signal that has the desired frequency and duration. Okay, and once we are done setting up this list node, we simply play the samples in that list by making a call to the play samples function from Std Audio, and we give it node as an argument, and it plays those samples. And once that is done, we go back and read the next pair of numbers. Okay, and then do the same thing. We digitize it and we play it. Get the next pair of numbers, digitize it, play it, and so on until we see the end of file signal, which is when we are out of the while loop, and we flush the audio by making a call to the wait function from Std Audio and terminate the program. Here is some input saved for this program, saved in a file called elise.txt, and I'm just showing you the first 5 lines of that file using this Unix command called head. So what are we looking at here? Well, the first column is the pitch information and the second column is the duration information. So we're saying the first note that we want to play has pitch 7 and 0.125 seconds for duration. And then we are saying I want a sound of pitch 6 and duration 0.125 seconds, and so on and so on and so on. Right? And then we can run this program by saying python 3 play that tune.py, and we can give this file elise.txt as standard input using the redirection operator less than. Right? So when we do this, this becomes standard input to this program. Standard input. And what would the program do? It would simply play the sounds in this file. All right. And here is, and if you actually end up running this program, here is how it would sound like. Okay, so so that's a nice program that shows you how you use the functions from the Std Audio module to create and manipulate sound signals. Right? So with that, we conclude this lecture. Thanks for watching, and thanks for your time.